in this video we're going to look at solving logarithmic equations. So I've done a few videos already on logarithms, so be sure to check those out if you need some background information. Also be sure to like, subscribe, share with somebody if you enjoy this video, if it helps. So now, solving logarithmic equations, the first thing we have to understand is there are two types. Okay, two types of equations that you're going to deal with when you're doing a logarithmic equation. So let's start with type 1 and go ahead and jump into this. So type 1 is when you have a logarithm equal to a logarithm. So essentially you have a logarithm on both sides. Okay. Now there's basically a one-to-one property that says if that happens, here's our steps. The first step is to condense. So we want to make sure we condense each side, which means we need to make sure there's a single logarithm on both sides. So once again, you want a log equal to a log. And if you need help with the condensing, I have a video that I've uploaded over that, so be sure to check that out. So then once again, our second step is to use this one-to-one property, and we can say, all right, if a log's equal to a log, then we can cancel the logarithms and we can take out what's inside. All right, so then that's step 3, or I guess that leads us to step 3, which is to now solve. Now, I would make sure to write this down. There can be extraneous solutions. I'll dive more into that in a second, but essentially an extraneous solution means it doesn't really work. When we solve the problem, the x value we get, or the variable value we get, is a value. However, when we plug it back into our equation, it doesn't work. And it'll make more sense when we cover it. So those are the steps. So now let's actually look at a problem. So let's say we have log base 5 of 5x plus 9 equal to log base 5 of 6x. All right, so now the key to type 1 is we also want to make sure that we have the same log and base, which we do here on this example. We have log base 5. Now, once again, our first step is to condense, but we already have a single logarithm on each side, and there's nothing multiplied in front of these logarithms, so this equation already has both sides condensed. So we're good on the condensing. So now we want to use this one-to-one property that basically says as long as this log base 5 and this log base 5 are the same, we can cancel the log base 5s, and we end up with 5x plus 9 equals 6x. So whatever's being evaluated here, you just take out and you set those two things equal to each other. And then you solve your equation. So we could subtract 5x, so then 9 equals x, so there's our answer. All right, now, just to double check that this is not extraneous, here's what we can't have. I'll just say extra or extreme period so that I don't misspell it. All right. So to check for extraneous solutions with a logarithm, here's the deal with a logarithm. A log can't be negative. So log can't be negative. So basically, here's what we're looking for. When we plug 9 into our problem here and here, we just want to make sure that that doesn't give us a negative number. All right, so if you notice 9, if we plugged it in right here, 5 times 9 plus 9 would be positive. 6 times 9 would be positive, so we're all good. So this checks out. X equals 9, it's not an extraneous solution. In a second, we'll look at an extraneous solution problem. All right, so now let's look at, actually we'll go ahead and do that now. So let's look at another problem. So log base 9. You could probably do this one on your own, so why don't you pause and try to do this one on your own. So log base 9 of 6 minus 3w equals log base 9 of negative 2w. All right, so once again, see if you could figure this out. All right, so we're going to condense each side, but if you notice, we have a log base 9, nothing multiplied in front, so we're good. We're condensed, which means we can drop the log base 9. So 6 minus 3w equals negative 2w. So now we just want to solve this equation. So plus 3w So 6 equals W. So these have worked out pretty nice for us thus far. Now that looks like our answer, but watch what happens when we try to plug this in. Once again, a logarithm can't be negative. All right, so log can't be negative. So if we plug in this 6 and we get either of these parentheses as a negative, that means we can't actually do it. So watch what happens. If we have log base 9 and we plug in a 6 into this, we will end up with, let's see, 6 minus 36 is a negative. That'd be negative 30. We cannot do log base 9 of negative 30. Like if you want to, you can even try to put this in your calculator and it will give you some kind of error. All right, so if that happens, that means that 6 is not a solution, so this problem has no solution. All right, so if you have an answer that looks like the answer and it actually doesn't work, then we call that extraneous and we have no solution. So, and actually I did this wrong. I don't know what I was talking about. It is a negative, but it's not negative 30. I just noticed that. Let's see, this would be 18, so it'd be negative 12. I don't know what I was doing in my head. All right, so this would be negative 12, which still doesn't work. All right, so this would still not work, so we'd still say no solution. So hopefully that explains the whole extraneous thing. If you plug your answer back in and you end up with a negative and you're trying to do the logarithm of a negative, that can't happen. All right, so now let's look at a problem where we need to condense. Let's say, and let's make it a difficult one. Let's see. How about we do, I guess there's not really that many that are super difficult. All right, let's do this. Oh, here we go. Here's a good one. All right. Log base 3 of 2p minus 5 equals 2 times log base 3 of 6 minus log base 3 of 4. All right, so now see if you could first condense this. All right, so see if you could condense this because that's our first step, and then we'll move forward after that. All right, so if you look on the right side, the log base 3's, we have 2 of those, and we have this multiplied in front. So once again, if you need to, go back and look at it may be the last video I uploaded about condensing and expanding, and specifically the condensing, because we need to condense here with this 2 times and this minus. And you always want to do the 2 times part before you do any of the adding or subtracting, okay? So first thing we need to do is make sure we know how to handle this 2. And if a 2 is multiplied in front of a logarithm, you can condense this by making 2 the exponent for that 6. So this would become log base 3 of 6 to the second power. And 6 to the second power would be 36. And then we would have our minus log base 3 of 4. All right, so now we need to continue condensing because we want to be left with a single logarithm on each side. So now we have subtraction, and remember subtraction tells us when we condense to divide. So we're going to say log base 3 of 36 divided by 4, which is 9. So now here's what we have. Log base 3 of 2p minus 5 equals log base 3 of 9. And now we can solve this because we can say, okay, the one-to-one property says when I get a single log equal to a single log with the same base, I can cancel those. So now 2p minus 5 equals 9. And we can solve that, which I will start over just so I have room. All right, so 2p minus 5 equals 9. All right, so now we just solve this like a normal equation. The only thing is once we get finished solving, so plus 5, we want to make sure that we check and see if this is an extraneous solution, which it could be, could not be, it all just varies. So p equals 7, and if we plug that in, let's just take a look. We just want to make sure that when we are plugging it in, we don't want any negatives. So let's see here. Equals, well, on the right side, there was no p-value anyway, so that part's good. The right side's good. All right, so all we need to do is plug this into the left. If I do 2 times 7, that's 14 minus 5. That gives us a positive, so we're good to go. This is an actual solution. All right, once again, logarithms cannot be negative. All right, so just for the sake of keeping this video as short as possible, let's go ahead to type 2. So now type 2 is a little bit more complicated because we no longer have a log equal to a log. We have a log equal to a number, or it could be equal to an expression or something like that. But essentially, we're going to end up here with no log on both sides, which means we don't have the opportunity to cancel our logarithms. All right, so that's the main difference between type 2. So let's go over the steps for type 2. The first step is you want to condense and isolate your logarithm. So make sure that we condense our log, and we have to make sure we have our logarithm on one side, which I think the examples we're going to do, the logarithm will be on one side. Then our second step is to rewrite our logarithm in exponential form. So rewrite in exponential form, which once again I've uploaded videos over doing that, so check those out if you need a refresher. And then step 3 is that we're going to solve, and then we'll check for extraneous solutions again. So check for extraneous solutions. All right. So those are the steps, and let's take a look at those. And I'm probably going to stick with more of the basic examples. There are examples where you can get into having one, well, you can end up with examples that need to be factored, but for this video, I'm just going to keep it basic. So how about we do, let's see, we've got log base 2 of x minus 4 equals 6. So hopefully you can tell immediately this has to be type 2 because there's no log on this side, which means we don't have that opportunity to cancel this log base 2 out. But what we can do is we can condense and isolate this logarithm, which it is condensed and it is isolated. So now we can rewrite this in exponential form, which is b to the x equals a. So we're going to say 2 to the 6th power equals x minus 4, because our base for our logarithm is b, so that's our b value. A is this entire expression x minus 4, and then x is this 6 on the right side. So now we can use this and we can say, okay, this is 64 equals x minus 4, and now we can solve. So you can see that we got rid of this logarithm, but we did it a different way. We did it by using exponential form. All right, so then 68 equals x, and I believe that would work. Let's just double check it. If we plug it back in, we have to make sure we don't get a negative. 68, let's see, 68 minus 4 would be 64, so it would work. All right, so now let's look at another problem just so you can see it. And we'll see, maybe I'll do a complex problem just so you can have it. We'll see. We'll see how we're looking time-wise. All right, so log base 3, 4x plus 8. Don't know what happened there. 8 equals, no, minus 7 equals 3. All right, take a shot at that. So once again, you can tell immediately that we don't have a log on both sides. So the first thing we need to do is try to condense, which this is already condensed. Then we want to get rid of this minus 7 because we also need to isolate. So how would we get rid of minus 7? We would add 7. All right, so now we would say log base 3 of 4x plus 8 equals 10. So now once again, if you don't have a log on both sides, this log base 3 can't be canceled with the one-to-one property. So instead of doing that, we're going to rewrite this in exponential form. B to the x equals a, and that should allow us to solve this. Let's see what happens. Let's see, 3 to the 10th power equals, no, 10 to the, hold on, did I write this down right? Oh, I didn't actually. Well, that's okay, we can do it like this. So 3 to the 10th power is going to be equal to 4x plus 8, which I'll need my calculator for this because I wrote the problem down wrong, but it's okay. All right, so then 3 to the 10th power, let's see, what would that give us? That would give us, I guess that would be a super big number, wouldn't it? Let me see. Actually, let's do this to make my life easier. Go back real fast. This is supposed to be a -3. All right, cool. Now I can make this a lot easier for me. Maybe not you, but for me. All right, so now this would actually give us log base 3 of 4x plus 8 equals 4. There we go. All right, so now we rewrite this in exponential form. 3 to the 4th equals 4x plus 8. All right, now that fixed it. So we're going to end up with, let's see, 3 to the 4th is 81 equals 4x plus 8. And now we just want to solve this equation. All right, so once again, if you don't have a log on both sides, you have to isolate and condense your logarithm, which we did, and then we rewrite in exponential form. So now let's go from here and let's see, 81 equals 4x plus 8. Then we would subtract 8 because we want to get our x by itself. We would say 73 equals 4x, and then we would divide by 4, and I don't think that can be reduced at all, which, I mean, it's a crazy looking number, but it'll be okay. 73 over 4. And if you plug that back into our original problem, essentially we just want to make sure that this log base 3 of 4x plus 8, we want to make sure that that doesn't end up being negative, which it would not end up being negative, so we're good to go. All right. Now, just for the sake of giving you one that's maybe a little bit more complicated, let me show you one more, but like I said, I want to make this a more basic video, but let's just do one that's a little bit more complicated just so you can see, just in case. All right, so 2 times log of x minus log of 4 equals 2. All right, so now let's condense this. So first, we have to deal with this 2 that's being multiplied, and it's going to become the exponent for x. So log x squared minus log 4 equals 2. So now we have an issue here again. We still don't have our logarithm isolated, but subtraction means divide. So this is going to become log x squared divided by 4 equals 2. So now we can rewrite this in exponential form, because once again, there's no log on the right side to cancel out this log. So if we rewrite it in exponential form, we would say 10, because remember, if there's a log, the understood base is 10. So it would be 10 to the second power equals x squared over 4. And now we could solve this, which I'll go through this one a little bit quicker because I know a lot of people probably don't care about the complex version, but that's okay. All right, so 100 equals x squared to the 4th, or x squared over 4. And now we're going to multiply by 4, multiply by 4. So 400 equals x squared. Now remember, if we have just an x squared, we could actually solve this by square rooting both sides. Just remember that we have to add in plus or minus. So we're going to say x equals plus or minus the square root of 400, which would be 20. So x equals plus or minus 20, which essentially means x could be negative 20 or positive 20. Now, here's where you need to look back at the beginning of our problem, because if you remember, we had 2 times log base, or log of x. If I were to plug in a negative 20 for x, that would be a negative logarithm, and that can't happen. So the answer is actually just x equals 20. So I know this last example was maybe a little bit more complex, but if you don't need it, who cares? You could skip through it. So there are, once again, remember there are 2 types of logarithms, okay? We have, well, logarithmic equations. We have a log equal to a log, which means eventually you're going to be able to cancel those logarithms. And then type 2 is when you have a log equal to a number, which means you're going to need exponential form for that. All right, so leave a comment if you have any questions. I can try to help out. If you dive into more advanced examples and get stuck, like I said, leave a comment. I can try to help out.